So I'm going to do my best to explain the vertical and horizontal stretch or compression of a function. This tends to be the more difficult one to understand, so you might want to pause the video and take notes at any point and rewind as you need. So a vertical stretch is exactly what it sounds like. It's like taking a function and stretching it vertically from bottom to top. So you have a rubber band and you're stretching it vertically. A vertical compression is the opposite. It's compressing or pushing the function down towards the x-axis. And for vertical stretch or compression, we use this notation here. So we're going to multiply a constant value a by the function. So this tends to be the one that people gravitate towards. It's a little easier to understand. Whereas with a horizontal stretch, we have, or compression, we use this formula here, f of 1 over b times the x value. And so we have these two values, a and b, and those are our constants that help us understand this horizontal stretch and compression and vertical stretch and compression. However, the horizontal one is like taking a piece of bubble gum and stretching it left and right. This is called a stretch. So we expect our function to stretch to the left and right along the x-axis. Okay, and we also know that a horizontal compression is going to be pushing that function towards the y-axis. All right. If I were to tell you, let's do a vertical stretch of the function f of x equals x squared, and I said let's do a vertical stretch of a factor of 2, what this really means is we are going to multiply f of x by 2. And that would simply look like 2 times x squared. Pretty simple. So maybe we have a new function called g of x, and that equals 2 times x squared. And that we say is a vertical stretch by a factor of 2 of the function f of x. So that's what g of x equals. And similarly, if we do a vertical compression of a factor of 1/2, well, our a value is just going to equal 1/2, and we are going to multiply 1/2 times f of x, which will equal 1/2 times x squared. So maybe we have a new function called h of x, which is a vertical compression of a factor of 1/2, and that's what it should look like, just like that. Now, if you're going to look at the graphs of these two, this is what it looks like. Okay, so the black graph is going to be f of x. And again, back here we called that first one g of x, the vertical stretch by a factor of 2 is going to be g of x, which is going to equal 2x squared. And you can see it looks like we took f of x and we pulled it up, right? We pulled it up along the y-axis to stretch it out, just like a rubber band. And if we did a vertical compression of 1/2, we would get something that looked like this, where the black function there, again, is just our f of x. It's our parent function, the parent quadratic function. But this light blue one here is going to be our, what did we call it? Oh yeah, h of x. So that'll be h of x, which equals 1/2 times x squared. So it looks like it's a vertical compression. That means we're compressing it towards the x-axis. That's the compression. whereas this one looks like we're pulling it up. The vertical stretch looks like we're pulling that black function, the f of x equals x squared, along the y-axis. So the one that people have a little bit more difficulty understanding or kind of kicking in is called the horizontal stretch or compression. If we do a horizontal stretch of a factor of 2, we have to go back to that notation for this, which is f of 1 over b times x. Now, in this case, b is equal to 2, right? So that means for all the x values, this is going to look something like this. F of 1 over b, here, let's do it this way. This is going to equal, all the x values are going to have a 1 over 2, because b is 2 times x squared. All right? We know that b is 2. Right? Now, it's basically a reciprocal. So if the horizontal stretch is 2, the reciprocal of 2 is 1/2. Now, let's define this function as, say, h of x. And that's going to equal 1/2 times x squared. Well, we have to do the math. We have to simplify this. This is 1/2 x times 1/2 x, which is equal to 1/4 x squared. So we have a new function, which is a horizontal stretch of 2 of f of x, and it is h of x, just like that. Okay. Horizontal compression, let's say we do a horizontal compression of 1/2. Now here's where it gets real tricky. We're still using the formula or the notation f of 1 over b. X is a horizontal stretch or compression. Our b value equals 1/2. So f of 1 over 2 x is what we need to find, and that's going to be, again, all the x's that we have we're going to replace with 1 over 2. Well, if you remember the keep, switch, flip, that's 1 divided by 1 over 2, which is 1 times 2 over 1, which is going to equal 2, right? Keep, switch, flip. All right, so what we're going to do is just replace that with f of 2x. Okay, so that's easy enough. Everywhere we have an x, we're going to replace it with a 2x, and we're going to square that because that is the function right up here. So we can do that. Let's define that as n of x. Okay, so n of x is going to be f of 1 over 2x, and that's going to equal 2x times 2x, which is equal to 4x squared. So that's our new function. Okay, this is n of x, the horizontal compression of 1/2 of f of x. Okay, all right. So the last bit I want to show you, again, over here we had defined, h of x and n of x, right? H of x was a horizontal stretch, n of x was a horizontal compression. This is n of x is equal to 4x squared. And this one was, what did we say again? H of x. So this is h of x, which was 1 over 4x squared. And again, the black one, the black function, is just our f of x. So if you were to graph these, this is what it would look like. You can see a horizontal stretch is literally going and taking that black function, f of x, and stretching it all the way, let's see, by a factor of 2, away from the y-axis. And the horizontal compression is the opposite. It's pushing it towards the y-axis. So it's squishing it towards the y-axis. Okay, and that's by a factor of 1/2. So that's how you have it. I'd like you to try to review this video if you can. And one thing that is very interesting is horizontal compression is like vertical stretch. That's something to remember. And vice versa. Vertical compression is like horizontal stretch. So I hope you took some good notes. Oh, yeah, that's right. Yeah. They're kind of equal but opposite. But you have to do the algebra to really figure out what's going on with these coefficients that are in front of your terms there.